This is Lesson 10B, Unit 11, Titrating a Weak Base, pH Calculations. So we're titrating a weak base with a strong acid, and here's a curve here. There's our starting sample. We've got 100 mLs of 0.1 molar CH3NH2. We've got a value for Kb, and we're titrating it with 0.25 molar nitric acid. We're going to calculate the pH after adding these various volumes right here. Now originally I was going to put you in groups during class and you'd be going off to tables to work this, but obviously with the coronavirus that's not feasible. So what I want you to do is go get a sheet, actually about 2 sheets, maybe 3 sheets of paper. Okay, come back with them because we're going to be working these problems separately. So I want you to pause the video, make sure you've got about 3 pages of notebook paper with you. All right, let's start up again. Okay, so some hints as we start to work through these. At 0 mLs, all we have present is CH3NH2. I'm going to abbreviate this NH2. Remember that this is our A-. So we're going to establish an equilibrium with H2O. Once we get past this point, all other points are first going to be worked as a limiting reagent problem, meaning we'll be using BCA tables. Once we're using in our buffer region, so there's our buffer region here, as long as we're in our buffer region, we'll be able to use pH equals pKa plus log A minus over HA. Now, remember that this value up here is Kb, so we're going to have to calculate our pKa in order to use this value right here. So that's something that we want to get done fairly quickly. Okay, so I want you to, I'm going to pause the video again because I'm going to start in on calculations. Okay, at 0 mLs, all we have present is the 0.1 molar of the amine with our Kb value. So I've set up an ice table, which should look very familiar to you. Notice that we are producing hydroxide ion in the equilibrium. So, and I'm dropping trailing zeros here just to keep things simple. So we end up with our value for X is going to be the hydroxide ion concentration. We put in our Kb value, we calculate that X is the hydroxide ion concentration. It's 6.08 times 10 to the negative third, which means that our pOH is 2.21 and our pH is 11.78. Okay, let's take a look at our next problem. We're going to have 100 mLs of 0.1 molar RNH2 plus 10 mLs of 0.325 molar HNO3. All right, so we have the 100 mLs of 0.1 molar RNH2 and 10 mLs of 0.25 molar of the nitric acid. We have a Kb value. This is going to be a limiting reagent problem, so our reaction that we'll use for our BCA table is we have RNH2 plus H plus, we're just going to do the net reaction, 100% completion, RNH3 plus. We're going to use millimoles because it's going to make life a whole lot easier for us, so these are all going to be millimoles. So if we take 100 mLs times 0.1 molar, that gives us 10 millimoles here. Okay, so we have 10 millimoles of the RNH2, 2.5 millimoles of the hydronium, and nothing to start with. The H plus is our limiting reagent. So we're going to end up with 7.5 millimoles of the amine, none of the hydrogen, and 2.5 millimoles of the RNH3 plus. So now we have our buffer system. The RNH2 is our A minus, the RNH3 plus is our HA. So our equation is going to be pH equals pKa plus log, and we're going to have 7.5 over 2.5. Now we have to figure out what our pKa is, and what we're given is a value for Kb. So if we calculate pKb, that is equal to 3.43, which means that pKa is equal to 14 minus that, so that is 10.57. So now we substitute in, and we have that pH is equal to 10.57 plus log 7.5 over 2.5. And when we calculate that, we get that that is equal to 11.05. What's key here is that you recognize that you need to convert this Kb into pKb and then pKa, so you have to use the pKa here. All right, go ahead and pause the video before we move on to the next one. All right, we've calculated 0 mLs, 10 mLs, now we're on to 20 mLs. So now we have 100 mLs of the 0.1 molar RNH3, and we've added a total of 20 mLs of the 0.25 molar H+. There's our Kb values, and we calculated pKb and pKa in the previous problem. So once again, we're setting up a BCA table. So we're going to be losing hydronium ions, since that is our limiting reagent. So we end up with 5 millimoles, remember this is millimoles, none of the hydronium ion, and 5 millimoles of the ammonium ion. So all of these are millimoles. So we can use the equation pH equals pKa plus log A minus over HA. And since we have the same amount of each, it doesn't really matter which one we use, but let's be clear here. This is our A minus, and this is our HA. So we have pH is equal to 10.57 plus log 5 over 5. This is a 1-to-1 ratio, so this is going to be just the same value. So we have that our pH is equal to 10.57. This is the point that we can use to figure out Kb of the base. So we can use this to find Kb from an equivalence point. In this case, we knew what it was, but what we're just doing is reconfirming that when the amount of A minus equals the amount of HA, that's going to be equal to either your Ka or Kb value, depending on what you're looking at. We're going to pause again to get ready for the next one. All right, so we're ready to do the calculation for 40 mLs. So we're finding the pH of 100 mLs of the amine and 40 mLs of 0.25 molar nitric acid. We have the Kb value, which we calculated previously, along with pKb. We also calculated pKa earlier. I went ahead and calculated Ka because we're going to need it, and I just did that by taking 1 times 10 to the negative 14th divided by 3.7 times 10 to the negative 4th. So we have everything we need here. So we're going to initially set up a BCA table because we've got a limiting reagent problem. So we set this up. We have equal amounts of both, so neither one is the limiting reagent. So we're going to use up both the amine and the acid completely. We're going to end up with 10 millimoles of the RNH3 and no millimoles of the amine and the H+. So what we're going to have to do now is we're going to be setting up an equilibrium with RNH3+ in water. And so we're going to be making RNH2 and hydronium ion. And this will be an ICE table because we are talking about an equilibrium now, which means that we're going to need the starting molarity for the RNH3. So we have the millimoles here. So this is millimoles. Our total volume is equal to 100 plus 40 mLs. So our total volume equals 140 mLs. So what we can do is calculate down here that the molarity of RNH3 is equal to 10 divided by 140. So that's ml and millimole. And when we do that, we get a starting concentration of 0.0714 molar. So this will go 0.0714 molar. That's coming from here. Initially we have neither amine or the acid. Then we're going to start making X of each. So there's our completed ICE table. Now we're ready to use our value of Ka from right here, so 2.69 times 10 to the negative 11th is going to be equal to x squared over 0.0714, and let's put the approximately in there, so that's 0.0714. Actually, let me erase that so it's clear in the notes. So 0.0714. When we solve for x, remind ourselves that x is equal to our hydrogen ion concentration, and that is equal to 1.38 times 10 to the negative 6th. That is our hydrogen, so we can calculate our pH directly from that. So pH is the negative log of this value, and that ends up being 5.86. Okay, so that is our equivalence point. We have one more point to titrate, and that is at 60 ml. So let me get that, make sure that's on screen. I'm going to pause one more time to set that up. Okay, we're almost done. We're on the last one. We have titrated at 0 mLs. These are the pH values. 10 mLs, 20 mLs, 40 mLs, and now we are on 60 mLs. So we're finding the pH of 100 mLs of 0.1 molar of the amine and 60 mLs of 0.25 molar nitric acid. So I've set up the BCA table for millimoles. I've got our various constants that we established earlier. So we start off with 10 millimoles of the amine, 15 millimoles of the hydrogen ion. So now our amine is our limiting reagent, and we end up with none of the amine left. We have 5 millimoles left of the hydronium ion, and we've got 10 millimoles of the ammonium salt. Now, if we're looking at the final pH, the ammonium salt will cause the solution to be slightly acidic, but the hydronium ion here is going to control the pH. So our hydronium ion is going to control the pH. So we need to figure out the molarity of the hydrogen ion. So we're going to have 5 millimoles, and we need to have it over our total volume. Our total volume is going to be 100 plus 60, so 160 mLs. When we calculate that, the concentration is 0.03125 molarity H plus. We take the negative log of that, and the pH is equal to 1.51. So that is our final value. So once again, you've set up a BCA table, but once we are past the end point, and we have excess reagent. It is the excess hydronium ion that's going to control the pH, and this value will just continue to increase as we increase the moles of hydronium ion. That's it. We have finished titrating the weak base with the strong acid.